Okay. Good morning. It's a pleasure for us. I'm Kalinka. I'm the Vice Deputy of the ICMC, and it's a big pleasure to be here today to start the first ICMC workshop on recent advances in computational mechanics for industry, and workshop that is in honor of our professor, Gustavo Buscaglia. It's really, really good to have you here. I told to Mariana that it's really good to have you here for this workshop and with us at ICMC. So it's really good to have you all. ICMC, it's a great institute because of the professors and the students and all the employees that we have here. So hope that you enjoy not only the workshop, but all the guys, all the people that are here. And thank you all to come here. Thank you to AUSAS and all the organizers of this workshop. And again, hope you enjoyed it. Thanks.
Okay, thank you. Good morning. Well, I would like also to thank everyone for being here. I know that it's not easy to reach San Carlos. It's quite far away from Sao Paulo, and well, we have to take a car, and it's a very long trip. I just want to make some announcements. Can you, Paulinho, can you project the screen? Yeah. Well, it doesn't matter. These are our sponsors. This is our Institute of Mathematical Science and CMI, which is the Center for Mathematics Applied to Industry, which is financing most part of the event. This is a very big project, which is led by Professor José Cuminato, who was very generous in giving the money to invite most of you. And this is funded by FAPESP, which is our agency from the state of São Paulo. And we also would like to thank CENPQ, which also is providing some money to organize the event. And well, this is, then I will give more acknowledgements at the end of the event, but I would like in principle to acknowledge the people from the events section who is in the organization, in the front desk. If someone didn't make the registration, please go there when we go to the coffee break and take your badge. Then if you have a poster, you can go at the moment of the coffee break to put your poster. You will see that there is a small paper inside. You can vote for the best paper. This is not compulsory, but if you want to vote, you will help us to decide which is the best poster. There will be two categories, undergrad and graduate students or researchers. So if you want to put your vote, there will be some place to deposit your choice. Just to make a mark in that paper. And well, that's all basically. Don't hesitate to contact me if you need anything. Then we will provide certificates for the participants at the end of the event. We will send them by email. And well, that's the only thing I wanted to say. So let's wait perhaps just a few minutes. Oh, we are almost in time. we can start with the first talk of the workshop, which is the one from Reinhard Lohner. I will open here. There, okay. Well, I will introduce Reinhard Lohner. Let me see my notes because he has a very extensive research. So, Professor Reinhard Lohner is the head of the CFD Center at the College of Sciences and of George Mason University, which is in Fairfax, Virginia. It's close to Washington. He received the Master in Mechanical Engineering from Universitat Braunschweig. I don't know the pronunciation, it's German. And a PhD in Civil Engineering from the University College of Swansea in Wales, where he studied under the supervision of Ken Morgan and Sienkiewicz. His areas of interest include numerical methods, solvers, grid generation, parallel computing, visualization, fluid structure interaction, so on. These are very long list of topics he addressed in his research. I don't want to delay it anymore, and I would like to thank Professor Reinhard for coming here and giving us this talk.
Thank you very much. It's a great honor to be here, and it's also a great honor to be the first one. I hope I can do due justice to that. I think that Gustavo and I go back quite a while. I think the first time was in Bariloche, but I can't remember the year, so that just shows my age. Okay. All right, so the topic is high-fidelity digital twins, and this is something, let's see if this works. How do I move this thing? Doesn't seem...
There is a power button beside the pointer.
Yeah, I know. Okay. Ahora sí. Okay. All right. If I stand here, it's because I've had the great fortune with working with a lot of people over the years, and I just would like to acknowledge some of them here. My team at GMU, then the team in Braunschweig, which we've been working on this subject for the last 2 years. So this is an outline. First of all, what is a digital twin? Why now? And then how do we detect weaknesses in structures? How do we select forces, sensors, and some open questions? So what is a digital twin? There are many definitions of this. This is one possible definition that I've taken from the AIAA, which is one of the few organizations that has sat down and actually defined what they want to mean when they say digital twin. And you can see it's a sort of virtual information construct that tries to mimic reality. And of course, the big important thing that is new is the feedback from sensors back into the digital model, and then you make some conclusions about what is happening in reality. So if you try to visualize this, we have the real thing, like the bridge that you see on the left. We have a fairly detailed numerical model that is just schematized on the right. And then we compare with the sensors that we have installed, what we see in reality and what we think is happening to the structure. And then we do decisions as to maintenance or repair or something that we have to do. So we have a set of standard forces. These forces would give us expected displacements. The sensors measure something else. And so with that, we can infer the state of the system and say this part of the system is weakened or damaged or something. So compared to what we were doing traditionally you were doing a finite element model before you were building the bridge, and then you never touched it again. So you build the thing and then you follow it up. The next level up of this would be to say, okay, I'm going to have the abstraction, my model, but then I go back to reality and check if really what has been built is actually what I have in the model, because during building things change and we may not have the steel that we thought we had or the concrete that we have. But in the digital twin, of course, we go back and forth the whole time. So this is let's say, the thing. So the question is, why is it happening now? Well, we have the digital twin as a product of these mega trends that we have. The first one is that we have, for most of the high value objects that we build today, a very detailed CAD and finite element model or some kind of digital model of it. We have, in most cases, we pre-compute, then we build, and then we have sensors everywhere. If you think about sensors, it's rumored that about 1/6 of the German GDP is purely based on sensors. And if you think about the sensors that are in your car or anywhere else, or even in your iPhone, it's a huge number. Okay, so they're everywhere, and we can measure a lot of things all the time. So if you look at civil engineering at this bridge, for example, you can see a long, very long list there of possible sensors. And if you look at the actual thing at the bottom, so if you look at this bridge here, you can see a laser measuring device here that can measure the whole displacement of this bridge. And what you do is you do it at a certain time of the year so that you always have the same temperature, no wind, calm night. You measure the displacement with a standard set of loads that you carry over the bridge, and you can measure the displacement to within 1/10 of a millimeter. So it's a very, very precise measurement that you can do every 6 months or every year, and then you can infer the state of the system. And this is particularly important for concrete, where you may have the damage inside the system and you may not be able to see it from the outside. If you think about bridges of the future or concrete of the future, you can see this is how they will look. They will have these fiber optic sensors inside, and you will have basically a 3D measuring field that you have inside your structure. So then the question is, how do you operate this? Well, we have a digital copy of whatever it is, the object. It could be you as a patient, or it could be a process, a production process. Then we equip these things with sensors, and with the data from the sensors and the models that we have, we infer the state, and then we update also, once we do a repair or maintenance, then we update the digital model accordingly. So what are let's say, the great expectations of a new technology? Always there's this big hype, and really what is it that people try to sell when they sell a digital twin? Well, we think we're going to get increased safety because we're going to know the state of the system in a much better way. We think that we're going to increase the comfort for consumer products, longer life cycles. This is very important if you think about also climate change. Concrete is one of the most polluting things that is out there. So if you can maintain bridges for a longer time, that's very beneficial. You could optimally control processes, fabrication processes or something like that. And of course, you would have a reduced environmental footprint. So the question is now, what data, or what is let's say, the data that you want to put in that digital twin? So let's take a very simple case of civil engineering. Let's take a city. Okay, so at the highest level, you would say, I have so and so many buildings in so and so many places. But then you could say, well, let's take every building and enumerate the parts that are inside the building. And then you could go one level down and say, wait a minute, now what is the maintenance history of each one of these parts? And then you can go even further and say, okay, what is the CAD and the the finite element model of this system. And then you go into each one of the subdisciplines, structure, fluid, thermodynamics, etc. And so then you go down to the computational mechanics level, and you could think of having a very detailed digital model of basically everything that has a certain, from a certain value upwards. And that's going to happen. So basically a digital twin is not reality. It's an abstraction of the reality. And so therefore, you have to be careful what kind of data you have and also what kind of sensor you're going to put, because those things correlate one with the other. Okay, so you need to know what the abstraction level is. And then we may even have abstraction levels from the abstraction level. So you may have a detailed finite element model, and then you say, no, I'm going to abstract that further and take a ROM of that. Yeah? So that's, of course, all well known in circles of computational mechanics, but not widely. So the level of abstraction determines what kind of digital twin you're going to use, and also the type of sensors that you're going to have. Now, if you think about the amount of data that you're going to generate from all these sensors and all the digital twin runs that you're going to do, it's going to be very, very large. Okay, so this is, you have constant sensor data that comes. You have a constant update of digital twins. So you could think of these bridge runs that are running every night based on the sensors that you have. And so the question is who will store this data, and who will secure or ensure that data so that it's not hacked in or modified, and manage it, and so on and so forth. So this is a very large opportunity for Amazon Cloud and Microsoft and everybody else. Now, if you think about, let's say, the digital twin environment, let's say the most sophisticated digital twin that is out there is us. Okay, if you think about Amazon Prime, or if you think about Facebook, or if you think about WhatsApp or everybody else, they have a digital model of you, or a digital twin of you that is fairly good. In fact, it may know more about you than you yourself. Okay, so this is, the great discovery of the early 20th century, that our privacy is actually very valuable. Okay. So it's not a great intellectual jump, but this was the thing that made Google and Microsoft and everybody very rich. Okay, so these are the examples there at the bottom that you can see. Okay, so the motto is we know more about you than you, and we think of this as surveillance capitalism. And if you think, we had the Equality of Rights in 1789, we had the big discussion of production means that finished in 1989, and so the question is now who maintains and curates your private data, and that's an ongoing debate, and let's see if it takes another 200 years to figure that out or not. So going now more into the detection of weaknesses in structures, we know that all structures age. We know that the first world has a huge problem with infrastructure because most of it was rebuilt after the Second World War. And even in the United States, most of the highways were built after Eisenhower came back and saw the Autobahn in the United States, in Germany. So concrete ages after 70 years. So, 70 years have passed after the reconstruction, and now all those bridges are falling. Here are some examples of bridges that have collapsed. The most recent one in Dresden this year. And if you think about the number of bridges that need repair in the United States, it's over 200,000. In Germany, it's more than 30,000. So suddenly, civil engineering is, no longer such a, backward topic, but it's becoming a very hot topic. So the first question that you can ask is, given loads and measurements, can we infer the state of the material or the weakening? And so if we know or suspect the weakening, where should we reinforce? So this is, of course, a problem that is not new. It's been all over the place. And there have been many techniques developed to do this, most of it based on accelerometers, because that was the simplest sensor that you could install. There have been some efforts in the time domain, And of course, there was some work also of adjusting parameters, and there's work from Ladevez and Aubry from the late 1990s on this. Okay, so the assumptions that we're going to make in what follows is that we have a set of standard loads, n standard loads. So we go over the bridge with a certain number of trucks that have a certain weight, and we put them in a certain place at a certain temperature and no wind conditions, etc. Then we assume that the weakening can occur at any location. And we will describe the weakening with some field alpha. Alpha is a number between 0 and 1. 1 means the structure is as it was when it was built. 0 means it's destroyed, or there's no resistance left. And we assume that the deformations and strains are well described by a sufficiently detailed finite element model. We assume that we have sensors, and those sensors have some kind of limit in their signal to noise ratio, so they can only measure above a certain strain or above a certain displacement. And we also assume that the forces that we can apply are not completely arbitrary. Okay, so there's a set of forces, and that's it. Okay. So the idea is to obtain the weakening by optimization. So we assume that we have these loads and these displacements, and then you can write this cost function where you have put some weight between the the displacement that you measure and what you get out of your finite element approximation, or your strain that you measure and the strain that you get out of your finite element approximation. Okay, and of course this cost function whose free parameter is alpha is subject to the finite element discretization, and we have a system of equations where we assume that the individual stiffness matrices have been weakened or not by this parameter alpha. That is, so if we have 1 million elements, this is a problem of very high dimension. We have to determine 1 million parameters. Okay. So a standard way of doing that is you do that via adjoints, because you have so many free parameters. The only way that you can do this efficiently is via adjoints. So you write the Lagrangian functional, so you put the adjoint here, and so you get your original equations if you take the derivative with respect to the adjoint. If you take the derivative with respect to the displacements, you get the adjoint equation. And because this is mostly linear elasticity, K is the same as K transpose, so your cost is relatively modest when you compute that. And if you now look at the gradient with respect to the alphas, it's a very simple expression. All what you have to do is you take the element stiffness matrix and multiply by the transpose of the adjoint and the displacement, and that's it. Okay. So there are some very nice properties of this. I won't list all of them, but what is very nice about this, and we insist on this, is that we are not trying to simplify the detailed finite element model to make a reduced order model of this, but we can use the high fidelity digital twin, so the finite element description that we have from the origin. Now, this is not applicable to any application, to all applications, but if you have a bridge, you're not going to measure the bridge every hour. So if this run takes even a day to do, so be it. Okay, what is the economic cost of a bridge falling compared to even if you have to compute a day? Nothing. Okay, so so the optimization cycle is that for each force or measurement pair, we do these. We obtain first the deformation, that's the forward problem, then the adjoint, and then we obtain the gradients, we sum them up. If necessary, we smooth. Yes, we have to smooth because the gradient leaves an h to the -1, so you have to do some kind of smoothing, otherwise the thing doesn't work. And then you update the solution, and there are many ways of doing this. The displacements are easy to obtain from interpolation, from a finite element base, and for strains, you do first the derivatives and then you interpolate that. So now the question is, how do you choose these weights? There are a number of ways of choosing them. You can either do it based on local weights. There are some disadvantages of this. Then you can do average weights. There are also disadvantages to that. And then you can do a max and combine them. And the one that we use is these limited local weights. So we take the maximum displacement and try to bound that with some 1% of that or whatever it is. And then we take the local displacement that you have there. Okay, so the first set of questions is, okay, now you've written all of this down, does it work? Can it resolve multiple weakening regions? Which set of forces should you take, and which set of sensors? So let's start with a simple case. This is a crane done with FE Last. We have 10 measuring points. So here you can see the placement of the measuring points, and you assume that you have a weakening in the lower part of the crane, this part here, everything that you see in blue. And so here you do a gradient smoothing, of course, and you end up, this is after 10 iterations, this is after 400 iterations, you end up with the correct solution there. So it has detected that all of this has been weakened. And you can also see the difference here between the displacements between the original, so this is iteration 0 and iteration 100. Basically, they are one on top of each other, which means you've converged. You could also do it on the strains. So now we put the sensors in the elements here, and you can see here the exact solution, or this is what should have come out, and you can see here the weakening that the procedure obtained. So if you then, you can go one step further here. If you then assume that all of this has not been weakened, then you can take this out of the optimization problem, and of course with that you can sharpen the zone where things are weakened. Okay, this is a bridge. So we have truss elements here, a set of forces, and then we assume that this part here, this one element here has been rusted or has been weakened. You get the displacements, and then you can see what happens here if we have 36 sensors, or here only 8 sensors, and this, you can see that it correctly obtains the weakened member. But of course, because of the smoothing and because of you only have 8 sensors and you have all of these trusses here, so it's not well defined, it's not an exact definition, so you also get some weakening on the other parts here. But you can see that also that this is a non-convex problem. You can see how the convergence is. It sort of goes for a while, then it drops a lot, then it does nothing for a while, and then it keeps dropping because it's trying to find its right minimum there. This is another footbridge here, this done with Calculix. We only have one member here that has been weakened, and you can see that it obtains that very well. And this is the displacement field that you get for that. And this is the cost function coming down. This is a 2D case here with a uniform load. And this is, I'm just trying to show this here. This is the weakened part here. So now we put only one sensor and we get this as the result. We put 2 sensors and we get this. Then we put 6 sensors and we basically have it. And then if you keep upping the number of sensors, you get better and better results. But of course, at some points, this saturates, which is what you would expect. And what is notable is that you would say, wait a minute, if I only have 2 sensors, if you think about a truss, and the truss is fixed here, and I'm only pulling on this side, I only have 1 sensor, then the weakening could be anywhere in between. Because all I have is the deformation that I have here. And yet, because of the constraint of the elasticity equations, you can see that it detects between sensors here in a very good way. So this is the constraint that you have because of the elasticity equations that is working for you. Okay, so this is in 3D. So just showing that you can extend this to an arbitrary number of dimensions and elements and whatever. And okay, once you've done that, then you say, okay, let me try the Hoover Dam. This is a finite element model of that. And now we're going to have 51 sensors. And actually, the Hoover Dam has many more, because what you have in the dams is you have these filaments coming down where you put weights at the bottom. And then as the level of water goes up, you measure how much the deformation is at the bottom. And you have that in all different heights. So it's a fairly simple but quite precise measuring device that you have there. And so we have prescribed here the zone that has been weakened, and this is what is detected. And you can see here, this was the prescribed part, and this is where the the algorithm detected a weakening below 0.8 of the concrete. Okay, and this is a more realistic case here. This was actually something that was measured in Braunschweig. And you have a tendons here. So this is reinforced concrete with basically every part that you would need. And this is the damage region that we prescribed, which was actually done in this bridge. They put acid on top to weaken the concrete. And this is what is actually detected by the algorithm. So we're not perfect, but we're not bad either. And this is with pre-stressed concrete. So this is a fairly realistic case. Okay, so now the question is, which set of forces is the best one? And here the argument is a physics argument. I need to have a strain in order to say, well, has this part weakened or not? If I have a beam and all I have is one set of loads, let's say one deformation, and the beam in the middle has no strain, well, if that part is weakened or not, I will never be able to detect that. Okay, so I need to have a set of forces that always has a strain in the element, because otherwise I won't be able to do it. Okay, and so you do a recursive algorithm. You have your standard set of forces that you can apply to the structure, and you take the one that strains the most elements as the first force. Then you remove all those elements from contention, and then you go to the next set of force that has the most elements that are strained left. And so you do this recursively, and you find that after 1 or 2, 3 forces, that's it. You've strained all the elements. So this is a case here, the 3D case here. So we have 2 loads, and now depending on where you put the sensors, you can see that this side load already has all this green part here, but there are some elements that it doesn't strain well. And so if you put the second load, then it takes all of the other ones as well. The same algorithm you can apply to the set of sensors. And so the idea here is to try to detect the largest possible weakening region, and do that also with a recursive algorithm. You take the one that, you know, the sensor that detects the most weakened elements possible. You remove that sensor and all the elements that it sensed from contention, and then you do this recursively and build your set of sensors like that. Now, there are 2 ways of doing this, the forward and the adjoint. So forward-based, you would say that you have a little bit of weakening, and that will give you a change in displacement. You can compute that either directly or recursively, so with a couple of iterations. In most cases, in most of the papers that you see, they neglect this part here and just do it directly. And so for each of these weakened regions, you can see how many sensors are able to detect that weakened element. The other one is, of course, just to go back to this, you assume that this is given. So you already have the LU decomposition of your matrix, so computing this for each element is not that expensive. So it's basically the number of elements squared times the bandwidth, and you have to store m times the number of elements. There are 2 workarounds around this. So one is to group the elements, and that brings down n elements squared to something that is n element. And you can do the storage very efficiently if you store the sensing in powers of 2. So this is a fairly simple way of doing that. So there are other possible improvements as well, but I won't go into those. The second option is to do this adjoint-based. So you have a function, you desire the derivative, you do the augmented Lagrangian, and then based on that, you can take your derivatives. And so you can take the derivative according to the weakening of each one of the elements. Okay, so this again is sort of, you do for each element, again, so for each sensor, you can get how many elements are being sensed or not. And in this case, the CPU is less. But of course, if you assume that you can have a sensor in each element, then you end up with the same as you have with the forward. So here's a case with this plate with a hole in 3D. These are the 28 possible sensor locations. And then, so this is the target strength factor here with 120,000 elements for that. This is the computed strength factor with all of these sensors applied there. And then these are the sensors that are activated by the weakening of an element. So if I weaken this element here, you can see a high number of sensors is able to detect that. However, if I weaken this element here, none of the sensors is able to see it because they are on the right of all the sensors that are there. So if you have more deformation over there, none of the sensors is going to see it. Yeah. So then you can, let's see if this works. Oops, go here. Yes. So now you do an optimal sensor location. You say, I want to have a certain influence zone for each one of these sensors, and you end up with very few sensors. So each one of these sensors has a certain zone of influence. And then with only these 5 sensors, you can see you obtain the same zone of influence that you had before. And this is another case here with a connecting rod. You can see the CAD, the mesh, the displacements, etc. And these are the possible sensor locations. These are the optimal sensor locations. So these are sort of the number of sensors that are activated if you weaken an element in a certain zone. So the forces are applied here on the right. So if you weaken this element here, a lot of sensors can see that. If you weaken parts on the right, of course, less can see that. And so this is the weakening that you get with 10,000, discretization of 10,000 elements. This is 71,000 elements in there. Of course, the higher the number of elements, the more you zoom in. But if you take these very few optimal sensors, you can see you also get a very similar region there. And so you can get away with a lot less sensors. So this is, again, the result for that. And these are the convergence curves for the cost function. All right, so next set of open questions is, will it work for multiple damage region? Is the solution stable? Is it dependent on the initial solution? Can we do eigenmodes? Can we zoom in? Can it be extended to nonlinear materials? What happens if we have singularities? Does it work for reinforced concrete? What do we do with stochastic and UQ? And can we recover temperature field or other things? So, does it work for multiple? Well, let's try it. Okay, let's take this blade here. This is a Siemens blade that was measured extensively in the Netherlands. And let's assume that we have one region here. Yes, we can recover that, no problem. Now let's take 2 regions. So this one and that one, and you can see, yes, it recovers the 2 regions. So we've done multiple 4, 5, 8 regions. It does it. Okay. Is the solution stable? I think this is a much more important question here. So let's suppose that we start in the neighborhood of the exact solution. So here is the weakened part, and we start from, let's say, 0.2 here. Can we get to 0.1? And the answer is, it looks as if, yeah, so you can see we are between 0.1 and 1 here, and you only see blue here. But if you go from 0.9 to 1, then you can see that some of the other members are also between 0.9 and 1. They're not exactly at 1, okay? So you converge into the neighborhood, but it's not perfect, okay? If you start from 0.2, so now everything is great. So you're much closer, and you think, oof, yeah, now even if I go between 0.9 and 1, I only see 0.1 there, and I only see something that is above 0.9 for the other ones. But if you now go from 0.99 to 1, you can see that these are also, it's not perfect. It's not 1 and 0, but it's, in the region of 0.99 to 0. But you started from something that was very, very close to the exact solution. So it seems that in the neighborhood of the exact solution, things are stable. Once you get into the neighborhood, things are okay. But if we start from an arbitrary random field, things are not so nice, okay? And it's the usual situation. We have 8 sensors. We have 365 possible degrees of freedom. So there are multiple solutions to this. Yeah? So you can see that this is one of the possible multiple solutions that comes up, and your cost function has come down, and you think everything is great. But the advantage that we have is that we start from a state that we know. Okay, so the structure deteriorates slowly, so we are already very close from where we want to go. So this is sort of an artificial mathematical, case that just proves that this is a difficult problem. But in practice, we're going to have a much easier problem. Okay, so the next question that I had there, can it be extended to eigenmodes? Because eigenmodes, this is the simplest sensor possible. You have an accelerometer somewhere, and suddenly the frequency of the bridge has changed. Oof, something is wrong, but where? Okay, so let's suppose we have this case. These are the eigenmodes, and now you say, okay, if I only take one eigenmode and try to optimize, the weakening, this is the region that I get. If I take two, I get these two regions here. If I get three, things start to identify, to sharpen. And if I go to more, let's say we have 8 here, the limit, we have this weakening region and this weakening region. Say, wait a minute, what's going on? The top region is the one that is the exact region, and the bottom region is this one. Well, it turns out, if you look at the eigenmodes, whether the weakening happened at the top or the bottom, it doesn't change the eigenmode. Okay, so it detects both. And if you run this with Calculix or with any other finite element code, then it detects either one or the other depending on the eigenmode that you're using. So the eigenmodes can detect, but you have to be careful about the symmetries of the problem. Okay, so this is sort of the corollary. You would need another differentiator that could tell you if you're up or down. Yeah, I'm running out of time. So then the next question was the reduction of the search space. So here you can see what you can do is you start, everything is possible. So alpha can be anywhere between 0 and 1. Then you get a first solution that detects some region, and then you say, I'm going to block out all of the other ones. I know that nothing has weakened there, so I'm not going to have degrees of freedom for my optimizer to do that. And then you can see how you can sharpen that region. And in the end, you're only optimizing for these values that you have there. So your search space is much, much smaller and you converge much faster. So you can see here the convergence of this. If you have all of the degrees of freedom here, you flatten out after a certain degree. But if you sharpen, then you keep going and you keep going, and you can see you get a much sharper solution also. Okay, you can do the same for the Hoover Dam. So this is just to show that you can do it in 3D. So you start with everybody, then it sharpens it, and then you're only optimizing inside these gray clouds that you see here. Only those elements are considered further as you march towards the final solution. Okay, before I finish, I showed you things that work. I also want to show you things that don't work. Okay, I think one should keep honest about this. Okay, and so here's a case of a real bridge. This is the infinity bridge. You have elements that are 1D, 2D, and 3D here. So you have shells, plates, beams, and 3D elements all combined. And this is one of the typical solutions. And so now the question is, what happens if some part of this weakened? Well, let's suppose this is the target part here. And you can see we'll recover that very nicely. So I could stop here and you all go back and say, great. Well, not so great. If this part here weakens, this is what is detected. And it turns out that, as in many real finite element models, you have a hinge here that has been modeled as a fixed connection. So you get a singularity here, and you might also get a singularity there, and those singularities start polluting the solution. So one of the questions that we have to deal with that we haven't found a good solution is, how do you treat singularities? Now, elastoplastic you can do. Let me just see if I can go on. So this is the same problem now done elastoplastically, and it detects, so this region here has gone fully plastic, and you can detect the region. So, extending it to elastoplastic is not such a big deal. Okay, so I only have a couple of seconds left, so I just want to show you that you can recover temperature fields as well, so I just go over this. And you can also recover material parameters with the same technology. So it's the same forward, adjoint, and then you get your derivative, and for the material parameters, we do this numerically here. So because you may have some complex material with 25 free parameters, so if you want to do the analytical derivative of the stiffness matrix, you might as well do it numerically. Okay, so this is just to show that you can recover these elasticity parameters here. So this is elasticity, and then you can do the same nonlinear as well. Okay, so just show that. All right. So I've shown you an adjoint-based system identification procedure for structures. Smoothing is needed because the gradient lives in h to the -1. It seems to work. We've tried it with 3 different codes with all sorts of elements, 1D, 2D, 3D, even combined. We have a benchmark suite of regression tests that we run every night just to make sure that everything is working. We've developed some optimal force and sensor selection algorithms. There are many, many possible extensions that we are looking at. I'm a senior fellow at the TUM right now. We have a student working there. So this is collaboration with the TUM also right now. And I think digital twins are here to stay. There are some compelling advantages for safety, maintenance, and longevity. There are many, many scientific opportunities in there that go all the way from pre-processing, from CAD, to the forward problem, to the inverse optimization problem, and also the data handling problem, large data. And I also think that it's an opportunity for universities because you have to combine all of this in order to get this to work. So if you think about the development of a digital twin workforce for the future, you have to change the silo mentality of many universities. So because the person that is supposed to work efficiently with digital twins needs to have a background in numerics, a very solid background in the field, so a civil engineer or mechanical or whatever it is, but then it also needs the computer science, the statistics, the large data handling, and all the other parts. And that is difficult to combine in a university. Okay, happy birthday. I think this is a wonderful occasion to be here. I'm so glad that I could come. And so happy birthday. May God keep you and bless you and grant you many more years of happiness. Gustavo.
We have time for questions. Let me see. Hello. Anybody want something?
Well, thank you very much for a nice presentation, Reinald, and it's an honor to have you here. But going to the technical, it is very complicated to close a bridge and go with the tracks, position them here and there, and measure to compute this. It cannot be done online, just looking at how many tracks are. As the trucks are passing over the bridge,
yes.
Sometimes the bridge will be empty, sometimes...
Yes. If you think about the future, we are going to have automated traffic systems. If you think about self-driving cars, for sure. So you will know exactly how many cars are there. And if you think also about the pressure sensors that we will have in the tires, which most luxury cars already have, so you could also transmit the pressure that you have, and so you know the load from that. So yes, that problem can be automated. Right now, actually, bridges are closed and people go in and measure. I know for sure the train bridges in Germany, they close the track at night and then they go over with this and they actually measure. And the only other way that is done by law is that you have to put somebody that actually goes and goes with a hammer and checks the bridge by hand. And that is done every 3 years, and it's incredibly costly. And also, you close at least one lane of the bridge, because it's like a crane device where this person is hosted down, and then he's tied up. It looks like an alpine climber, and I mean, it's incredibly time consuming also to do a whole bridge. But if you have, for example, in the Alps, where you have a lot of salt and a lot of corrosion in the winter, you have to do it every 2-3 years. Yeah? And so it's incredibly expensive. Yeah, but yes, this in the future is going to be transmitted. All the cars will connect, and will connect centrally as well, and you will have the information. Yeah.
But and then after these measurements, you need a code that does that. Something that has to be implemented in as a protocol. For civil engineers.
Yes. Yeah. So you will need a very detailed finite element model of this. And if it runs overnight on a very large machine, so be it. Yeah, there's one bridge in Frankfurt that was very close to collapsing, and they had to close it. And I think the cost by now is $1 billion, $2 billion, something like that. It's an incredible cost, and also the people taking 40 minutes more to go to work and things like that. I mean, imagine Zárate Brazo Largo falls down. Or Rosario, yeah. I mean, actually, we had that problem in Argentina. There was a ship that hit the bridge of Zárate Brazo Largo. Yeah.
Any more questions? Well, let's thanks Reinhard again. Our next speaker is Christian Hefhard. He is a friend of us. We meet each other in the pandemic. We started to work together online, and then we finally meet each other recently with Gustavo. I will say a few words about him. Let me see my notes. 1 second. Yeah. Well, he's from Argentina. He had a degree in mechanical and aeronautical engineering from Instituto Universitario Aeronáutico. His doctorate in engineering science, where he developed numerical simulations of aeroelastic behavior of large horizontal axis wind turbines at the University of Universidad Nacional de Córdoba. And he obtained the habilitation, what we call here libre docencia, for statics and dynamics from the University of Leibniz in Hanover. He's a very young professor, he's full professor. He obtained the promotion in 2022. He's 41 years old. And well, he's now the director of the Bergen Offshore Wind Center in Norway, University of Bergen. And he's full professor at the Geophysical Institute of the University of Bergen. So it is a very, it's an honor to have you here, Christian. Thank you.
Yeah, thank you very much for the invitation to this seminar. It's really an honor for me to be here and to give a presentation commemorating your birthday. So we started to work recently. I think maybe I am the last one of the gang. So we started in 2020. And I learned already in these few years really a lot from you. So I am very thankful for that. And also for giving me the opportunity to exchange ideas. And now I am going to present a work that we are doing together since a while, and it's about data-driven computational mechanics. And this is a new computing paradigm that, beyond being new, also can be a key technology, simulation technology for digital twins. So in this presentation, I'm going to talk about a little bit on the formulation of the problem, the mathematical analysis, and also to present some examples to show the potentialities of this method. So basically, the motivation is what we do typically when we solve mechanical problems. We have a differential equation, we have boundary conditions, and also we have constitutive laws. So this is the case of a Darcy equation. We can have different constitutive laws, linear, nonlinear, and so on. And also we have the similar for elasticity. But we can consider, there are many problems that can be represented with this formalism. So now the idea is to see what happens if we don't have a constitutive law, and instead of that, we have data sets. So the idea is to try to reformulate these problems, and instead relying on constitutive equations, we use directly the data sets. But basically the idea is, of course, we have new buildings with new geometries and also with new materials, and we have standard modeling, structural assumptions that we can use. But if we consider this building is made of wood, and wood is not a traditional material, so we have properties that are going to change and evolve over the time. And let's say that we can measure the properties of this material, and when we measure, basically we are going to sample points on the constitutive manifold. If we have a perfect manifold, we are going to have something like we have on the top here. But if we consider reality, we are going to have something more like this. So we have uncertainty, we have errors in the sensors, errors in the sensor chain, and so on. So the question is now how we can combine these things together. So this is possible if we can formulate some optimization problem in such a way that we minimize some cost functions that is looking for the data points in the data sets, and also additional fields that are helping us to preserve equilibrium, compatibility, boundary conditions, and so on. So this is a little bit abstract, but basically the first thing that we need is a weak statement for the equilibrium. And this equation that we have here, this phi, is basically the balance equation combined with the compatibility equation. But here we have no information regarding the constitutive manifold. So this is something that we're going to use in order to constrain our optimization problem. So now, if we consider data sets, what we are going to have is something like this. We are going to have a collection of data that we are going to measure. And now, when we have a structure and we are applying loads, we are going to look for those data sets that are active in this system. So if we are having a structure in traction, typically we are not going to use the data that we have for compression. So something that we have to do is to determine what are the data sets that are active in this process. On the top of that, each data is going to be valid for a given region, so we need to determine the domain decomposition induced by the data. So now, combining all these things together, we can define something called discrete continuous nonlinear optimization problem, in which we have a cost function that is given by these proximity measures that are measuring the difference between the fields that are represented the internal state of the system and some extension of the data sets that we are going to use. So here, what we have, typically if we use a formulation for this kind of systems, we can look for the deformation and also for the stresses in L2. So one possibility is to try to extend the data by using approximation by simples, and this approximation by simples has enough power to approximate any function in LP. So so this is what we are going to use. So now what we have to do is to solve this problem in which we minimize these proximity measures, and also we have the term coming from the balance and also the compatibility. And if you can see here, we have a type of in-sub problem in which we need to optimize over continuous fields, and also we need to optimize over discrete fields. So basically, this is a topological optimization problem. And as you can imagine, this is very difficult, first of all, to analyze, and also very difficult to solve. So something that we are interested in first is to investigate what happens if this partition and domain decomposition are already provided. Basically, the idea is to solve this kind of problem, we are going to use alternating methods in which we take for fixed the elements from the data set, and we iterate over the continuous fields. And then when we have these continuous fields, we iterate over the data sets. And in this way, we need to have these suboptimal problems in which we are going to find the continuous fields. We need to have a problem that is well formulated and well posed. So, but basically what we are going to deal with is originally we have this domain, and then we are going to have a set of active data points and the corresponding partition. And we are going to take first this as a given, and then we are going to investigate the properties of the resulting problems. So here we have the possibility of formulating many problems with this formalism. So we can consider formulations in which we have, on the top of that, domain decomposition, without domain decomposition, using multiple primary fields and secondary fields and so on. So, but basically we have four formulations that we can derive from here. And then first what we do is to formulate the nonlinear problems, and then to analyze the nonlinear problems, we linearize, and then we use the QPLC theory in order to investigate the properties of this formulation. Then, you know, when we consider domain decomposition, also we need to add additional terms in order to introduce the forces made by the interface forces. Also, we need a restriction in order to have continuity over the domains, and also we need an additional constraint in order to have the boundary, the interface in equilibrium. So typically, we are going to split these families of formulations. One formulation in which we don't use domain decomposition, and other one in which we use domain decomposition. And therefore, we also need to have the trace or functions defined on the trace, and so on. But basically, this is the standard, or I will say, not the standard, I will say the simplest problem that you can formulate. So here you can see that we are having two fields. One is the displacement, and other is the stress. And then we are going to have a Lagrange multiplier, I will say, that is enforcing the continuity and also the balance in the system. Only the balance, sorry. And then we can see what we have to find is this X star, Y star, such is the argument that satisfies this in-sub condition. And basically, what we have to do is to define this phi zero, in which we use explicitly the strain as a function of the displacement. Then another problem that we can define is now using three fields. So if you are familiar with Hood-Bashitsu functionals or something like that, this is what we are using here, is one field for the displacement, one field for the strain, and another field for the stress. Then we are going to have two multipliers, one for the equilibrium, another for the compatibility. And then we can define this problem. Now, if we introduce the domain decomposition, things are becoming a little bit more tedious. And we are going to see that we have to define fields over each domain, and also we are going to have to define fields over the trace. And this also applies for the primal variables and for the dual variables. And at the end, we are going to have some formulation like this. And on the top of that, we are going to have these restrictions in which we are going to have the equilibrium, the compatibility. We are going to introduce the forces on the interfaces, the continuity, and also the balance on the interfaces. And here we can do things even a little bit more tedious if we also have displacement field defined on the traces. As you can see, we are formulating here in a nonlinear setting using P norms and so on. This is still very difficult to analyze, but something that we can do is to linearize the problem and then to recast this problem in something that we know very well. So we can use this theory. Basically, this is what the people working in optimization are using, but it's similar what we do in finite elements. It's essentially the same, but we have a quadratic program with linear constraints, and basically we can define bilinear forms and linear forms, and then if we have this optimization problem, we also are going to have optimality conditions, and these optimality conditions are well known for us. So basically, this problem is well posed if we have this bilinear form that is coercive in the kernel, in the right kernel of the constraint equation, and also the bilinear form B satisfy the IMSUB condition with left kernel having only the neutral element. So now it's time to simplify everything and to see how this abstract formulation can be expressed in something that we know very well. So here we have different spaces that we're going to use for the formulation without domain decomposition and with domain decomposition. But basically, let's start for the first problem. We have here only two domains, and we are going to approximate the fields, the extension of the data with these simple functions. Then we have here the displacement and the stress, and here we have the Lagrange multiplier due to the equilibrium. And here you can see we are going to minimize this cost function subject to this constraint, and this constraint is nothing else than the weak form of the equilibrium we know very well. Also, if we work a little bit with this equation, we have some further regularity. We can obtain the optimality conditions in strong form, and we are going to see that if the data is given, then we don't need to solve all the problem in one shot. We have two problems that we can solve in a separate way, and are problems that are well known, and we know how to solve very efficiently in the numerical setting. Then the second formulation, that is the formulation with which we are working right now, is the one in which we consider three primary fields: displacement, strain, and stress. And also we have two multipliers, one for the equilibrium and another one for the compatibility. And then we have here basically the equilibrium, and here we can see the compatibility condition between displacement and strain fields. Again, if we play a little bit with this equation, we can obtain the optimality conditions in a strong form. Also, we need further regularity conditions. And we can see the equations that we have here, and we can see that we can solve the first one, the second one, and the last one on one hand, and this one, the third one, and the fourth one on the other side. So we have two problems that we can solve separately. But this is because we linearize, so we don't have coupled terms. If we have, for instance, a deformation measure that is nonlinear, then we are going to have everything coupled, and then we need to solve everything in one shot. So here is the same, but this time with domain decomposition, using the continuity between the displacement field in one domain and the displacement in the other domain. So we are going to have only a multiplier for the constraint force enforcing continuity. So here we can see the term that is due to the work done by the force on the interface, and then the other is the one due to the continuity across the interface. Here, again, we are some further regularity, then we can obtain the conditions, the optimality conditions in strong form. And we can see that basically here we have the same that we had before, but for each domain, as expected, we are going to have also conditions in the interface, and also we are going to have the boundary conditions. And this is the last formulation in which what we have is a displacement function on the trace, and then we have the continuity is this field to the trace and this field to the trace. And then we can recognize that we have also this term, and also the forces on the interface should be in equilibrium, therefore we need the last term. Again, the same equations in each domain, but now we have extended interface conditions. So I'm not going to get in details with the analysis, but basically the result from the analytic point of view is that all these problems are solvable with unique solution. And on the top of that is that if the partitions are regular enough, all the formulations are equivalent. And basically what we do is we take the solution for the simplest problem, and then we map the solution from its space to the space of the other formulation, and this map should be continuous and injective. And then we try to replace this, and then basically we show that the formulations are equivalent if we get the same optimality conditions, or if the Lagrange functions for each formulation differ only in a constant. And this is what we could do. And then using the uniqueness of the solution, we have the implications in all directions, so all the formulations are equivalent. So now we are going to talk a little bit about how we can use this formulation in reality in the context of finite elements. And we are going to consider first the Darcy problem. And basically what we can derive from the constraint equations is a family, several families of formulations, and basically we are playing with the integration by parts. So the natural formulation is the one in which we look for the strain and the stress in L2. So this is the minimal regularity we can ask. And as in the way that we are doing the formulation, we don't have derivatives. But if we could have further regularity, then we can start integrating by parts, and then we have different formulations, and to each for each formulation, we are going also to have a different finite element setting that is more appropriate for that. So basically, we are considering a formulation A that is the natural formulation in which we require the lowest regularity on the strain and stress field. Then we are going to consider an equal order in which we use same functions for all the variables. Then we have a B formulation in which we integrate by part the first term and the compatibility term, and also the C in which we integrate only one, and in the D we are going to integrate the other one. And basically, so these are all the formulations that we are going to consider. Then I'm going to talk about the numerical properties of this formulation. But basically, something that we have to do as usual is to initialize our problem. And this is a tricky point, because these optimization problems are in the nonlinear setting, in general, non-convex problems. So basically, if we give an initial condition or initial guess that is close to the basin of attraction of a local minimum, then we are going to reach that local minimum, and we are not going to move forward. On the top of that, if we use alternating methods, it might happen that we can have some problem in which we have a partial minima, which means if we have a surface like this, we have here something flat, but we keep this fixed, and then if we see in the other direction, we move backwards or downwards. So the thing is, if we fix and we optimize in this plane, we are going to get stuck there, and then we are not going to move forward, and then that's the end of the solution. And this is not the solution that we are looking for. So we are always trying to look for a global minimum. So here what we did is, it is important to try our points to use data sets that are more or less realistic. We are not working now with experiments, but we are doing the best that we can do from the finite element point of view. So basically, we are solving a problem with a constitutive we know, a nonlinear one, then we generate points, we add some perturbation, and then we use these data sets. So one thing that we can do to initialize the simulation is, for instance, to try to identify a constitutive manifold that is smooth, with local representation, and then to try to solve a problem with a smooth constitutive in order to find some initial guess for the stress and the strain. And then after that, we look for the stress and the strains that are closest to those points that we obtained with this solution. And this is our initial guess. And then we are going to solve the fields for that data sets we have. So something that is quite important is here we are doing one-dimensional test, but basically if we have isometry in our problem, what we have to do is to distribute the data. And basically these are trajectories in SO3. So we take our data and then we have to distribute. So we can take 2p and we can divide 5, 10, and so on, and then we rotate the data. Because basically we are going to do an actual or very simple test, but to characterize something that is 2D or 3D. So we need in some form to complete our data sets. So here, if you can see, when we solve the smooth problem, we are going to have this partition. So this is the partition of our domain. And then this is the solution, the data-driven solution associated to this partition. Something else that we can do is to start playing with how we rotate this data. And we can see that, of course, as expected, if we have more points, then we are going to have a better solution. So we are going to see how the quality of the solution is improving by extending this one-dimensional data. So here we have more detail about the domain decomposition that is induced by the data sets we have. And something that is quite important is, so far we are playing with something that we don't know the exact solution, and it's important to be sure that our approach is compatible with the standard solution. So basically what happens if we use finite elements when h goes to 0 and with the number of points goes to infinite, we need to recover the classical solution. So for this, what we did is we constructed a manufactured solution, and then we are testing how our data-driven setting is converging towards that classical solution. So here we can see this is the pressure field, and here we have different data sets that we are using for this, and we are reporting the pressure profile in the diagonal. And this is what we can see. So we have the exact solution, and then we can see how for a fixed grid, if we increase the number of nodes, the data, how we are going to approach the classical solution. So this is something that we can do. So also, for the pressure, it works well, I will say, and for the flow, this is a little bit more difficult. So, but we can see here the different fields for the flow, and then we take the profile here, and we can see that with few data, the quality of the solution is not really good. But as we increase the number of solution, we are going to get closer. And then you can see also that in the numerical solution, we have some oscillations that are induced by the finite element setting we have. But basically, this is with fixed mesh. And then if we increase the number of elements and also we increase the number of data points, we are going to converge to the classical solution. And here, as is expected, we have these different formulations, and here we have the convergence plots for the pressure and also for the flow. And something that we were expecting at the beginning when we didn't understand very well the problem is that maybe the data can, in some form, stabilize the solution, and we can have a good approximation with formulation with equal order, but after having the equations and taking a look at the equations, we realize, of course, it doesn't work as usual. So basically, if we want to use a formulation of equal order, we need some kind of stabilization, as usual. So also something that is quite important is the robustness of the approach with respect to noise. So here we took the perfect constitutive law, and then we sampled some points, and we also add some noise, and we distributed the data in the space. And we can see that in general, the robustness of the solution is, I would say, pretty decent. And now I would like to present 2 or 3 slides regarding solid mechanics, but this is basically a solid in which we apply a load that is constant and a load that is a sort of Gaussian function. And then we have boundary conditions here in such a way that we allow the displacement in this direction and the displacement in this direction. And then we can see here, this is the solution, the classical solution. And now what we are doing is we are generating data. Also, what you do in reality, you do axial testing and also shear testing. And basically with this, we generated this artificial data. And then depending how we, the size of the sample in the direction, I will say, along the constitutive, and also how many replicates we have when we rotate, we are going to have solutions of different quality. And basically you can see how important it is to have a good balance between the additional points along the constitutive, and also how important are to have the rotations in order to have to capture the field over the solid in a proper way. And here what we have is the domain decomposition induced by the data. And you can see if we have few points, we are going to have some domain decomposition that is not nice. It's perfectly okay, because we are considering that we can represent over the composition in terms of the elements of the triangulation. But as we have more points, we are getting things that are more nice, I will say. Yeah, so just to finish the presentation, I would like to talk about opportunities. Currently, we are working with this principle in a project called Data-Driven Offshore. The idea is to use this data-driven technology in order to improve the predictive capabilities of simulations for wind turbines. And here the idea is to include the data, to use this approach to improve the predictive capability of the simulation models, and also to develop a digital twin that is, I will say, from the scientific point of view, rigorous. So if we have the real twin and we have the digital twin, then we can measure on the real twin, and then we can have a constant stream of information from the real to the digital twin. Then we can apply this approach, and then we are going to mimic the real asset. Something that is important with this technology is we are not using model update in any form, because in this approach, as we are taking the data directly, we eliminate completely the calibration of the model to the real data. Then also another project that is related is doctoral network, in which the idea is to use also digital twins for rotor blades, but the idea is instead using technologies like neural networks, we would like to use the equation of motion of the blades as a neural networks, and then we are going to train these models using real data. And the idea is with this, we would like to create new methods to design wind turbines. Just to give an example, if you want to buy a wind turbine today, the biggest wind turbine that you can order, maybe it takes 2-3 years to get delivered, is a turbine with 15 megawatts, and you have rotor diameters of 320 meters. But now there are companies designing big wind turbines with 20 megawatts, and we are talking already of 400 to 500 meters of diameter. And we expect with this to go beyond that, so we would like to enable design technology for 25 plus megawatts. And last and not least is also we have a project that is supported by Equinor. This is the company, the oil and gas company of Norway. Now they are investing a lot in renewable energy, and they are starting to build wind farms. And when we have a lot of wind farms, we are going to have aerodynamic interactions. And according to these aerodynamic interactions, we are going to have a reduction of performance. And also we are going to introduce loads that are not good for the structure and the integrity. So the idea is to develop fast models that can be used almost in real time in order to control these wind turbines. And for this, we are going to use reduced order models, typically boundary element methods, combined with neural networks. And the idea is not to replace everything with neural networks. We would like to model the wind turbine using physics, but when we move a little bit far away from the turbine, we can use neural networks in order to represent this behavior far away from the wind turbine. So I think this is the last slide, and thank you very much for your attention. So if you have some question, I will try to answer.
Well, there are questions. We have some time.
Thank you very much, Christian, for the nice presentation. You were very theoretical at the beginning, and in the end, you showed all those wind farms. That perhaps you can explain a little bit what is what is limiting the size of the wind farms and of the turbines? Is there knowledge needed for that? Safety? Digital twins will make bigger farms and bigger turbines possible?
I think digital twin is a great technology. The problem is if these digital twins are relying on a standard modeling, we are not going to get much more better. So we also need to use models that are more complex. And if you see the methods that are being used by the industry right now, so doing design with finite elements, solids and fluids as it should be, is just a distant dream in the future. So basically, they do only one CFD simulation at the end, just to check that things are more or less in order, but the design this is not part of that. So the models that we are using right now, they have some limitations, and the non-linearities are becoming more important. Also, the scalability is not trivial. So if we take in consideration floating wind turbines, we have the wind, we have the sea, we have the structure. Reynolds number, Fruit numbers, they are not good friends and things like that. So I think there are a lot of theory and models that are already there that can be used for that, but we need to talk to each other and try to migrate those methods that are already there in order to solve these very challenging problems. But this is my opinion.
Thank you, Christian. So when you talk about digital twin at the end of your presentation, to make a connection with your abstract presentation at the beginning, you're thinking of applying this abstract formulation to the fluid mechanics of the turbines, to the solid mechanics of the structural behavior of the blades, or to the form as a whole continuum that has strange interactions that cannot be modeled using a traditional constitutive model, because you have this long range and I mean, what is your expectation regarding your modeling applied to the problem that you put at the end of your presentation?
Yeah, so right now, the idea is to use this data-driven formulation for modeling the blades of the wind turbine. These are composite materials, very complex, and also they are very prone to degradation. And the idea is, if you are monitoring the structure and you are getting information about that, the digital twin based on this technology is going to degrade according to the data. So, of course, I am focusing not in the end-up application for control purpose or design, but the first idea is to show that this is already possible. And basically, we need to solve an optimization problem that is a little bit complicated, but if you initialize the problem in a proper way, you can increase the time, I will say you can reduce the computing time. And maybe it's something that can be viable in a few years from now. So I think that maybe 5 to 10 years, this could be something that can be used at industry. Also, this can be applied if you have the wind turbine. The floating substructure is a battle of concrete. 90 meters is continuously projected concrete. It's really amazing how they are doing this. And you know that concrete is changing the properties. So I think you need maybe 1 year in order to have 95% of the end life properties, and then you are going to have some degradations, and these wind turbines are going to be there for 30 years. So you need to deal in somehow with the degradation. And also, another thing, mooring lines. The anchoring lines, typically we use chains. They are very expensive. Now we want to use nylon polyester. And if you take a look the experimental data from this kind of ropes, you are going to see that there is no chance of representing this with any standard constitutive model. So there are a lot of applications there.
Are there any more questions? If not, let's send thanks to the speaker again. Thank you very much. And we have a coffee break. We start at 10:20, I think. I will ask you to come back.
Okay. The last speaker of this track will be Pablo Blanco. I will introduce him. Pablo Blanco is a researcher at the National Laboratory for Scientific Computing, LNCC. Also, he is head of the HemoLab, Hemodynamics Modeling Laboratory Group at the LNCC. He has been an affiliated member of the Brazilian Academy of Sciences, has published one book and over 100 refereed papers in scientific journals. He received an electromechanical engineering degree from the National University of Mar del Plata, Argentina, and his doctoral degree in science from the LNCC. His main research interest is the modeling and simulation of the cardiovascular system and scientific computing applied in the clinic. Pablo is responsible for leading the HemoLab group through the construction of the ultimate cardiovascular simulator known as ADAN, anatomically detailed arterial network model. Your time, Pablo.
Okay, thank you for the introduction. So the pointer is this one. Yeah. So this is joint work that we have been doing for over 15 years. Actually, we have not been working on this problem because we solved actually this problem some years ago together with Gustavo. I will talk about more about that. Enzo Dari, also, and another friend, Jorge Leiva from Balseiro Institute in Argentina. The photo that Adrian put about Belén in 2008, where we started writing the proposal for building this network that has been funding our research, also Gustavo's research for over 14 years now. We are renewing this network right now, this month, actually. So there is quite history here, and the question is, what did Gustavo do upon my career? So we had a nice talk before my PhD defense in 2008. I was very nervous because I just had heard stories about Gustavo and his roughness, apparent roughness. It was a sweet guy in the end. So, but I was nervous. We had very, very interesting exchange ideas during this talk. 2 hours where we were not discussing my PhD thesis, but we were discussing about the future. We had been working simultaneously on the coupling of dimensional heterogeneous models. This is 2D, 1D, 3D, and how to deal with this problem. We here in Brazil, I was working with Professor Feijó and Gustavo with Jorge Leiva at the Instituto Balseiro. We set some challenges even before I had made my defense, and we started working together. And the next is the result of this collaboration, very, very prolific collaboration. So this is the result of many years of work. The idea is to integrate different models of the cardiovascular system, the representation, the mathematical representation of different components for this system, because you are dealing with multiple scales, spatial and temporal scales. The representation into these components refers to the representation of different spatial scales, particularly. So this is routine in hemodynamic applications, how to deal with a model that has been isolated from the rest of the system. So you created artificial boundaries, and these artificial boundaries have an interplay with the rest of the system, which is not, which has where the two systems interact in a very strong way, because the local flow, the local blood flow can have a very strong effect on the behavior of the rest of the system, and vice versa. So the system, we started understanding the system as components assembled, black box components, and the idea is that this is strongly connected with the idea of black boxes. Black box codes, where you have developed specific codes for different mathematical models, for ordinary differential equations, one-dimensional partial differential equations, 2D, 3D, and so on. And you want to integrate all these black box codes all together. So you have blood flow in specific regions of your system where you want to understand, for instance, how wall shear stresses interact with the endothelial wall, and this is related to the risk of rupture of an aneurysm or to the risk of developing atherosclerotic plaque over the arterial wall, the thickening and the remodeling. And this is strongly affected by the boundary conditions that you define. And this is what people overlook mostly in this type of simulations. So small variations of the boundary conditions in this type of simulations lead to very strong deviations in the blood flow behavior inside these three-dimensional regions. And most importantly, when you are dealing with very large and important regions of the system, like in the case of for instance, the entire aorta artery, right? So on the other side, you have a wave propagation phenomena in the entire cardiovascular system, right? So the system spans thousands of vessels, where in this case, we are using a very simplistic representation of the system, and you have very different flow regimes in the different regions of the body. This arterial system, which is represented by one-dimensional models, is closed on the venous side by a zero-dimensional representation, a compartmental representation of the valves, the cardiac chambers, which are active elements. So you have a myriad of mathematical models, some of linear, some of very nonlinear, some have some stability conditions regarding time stepping. The other models have other concerns regarding the numerical methods that you apply to, like the one-dimensional models. And the idea was to avoid having access to the computational codes to implement these models in a monolithic way. We wanted to get rid of that. We had done that. We implemented at first everything monolithically, so we had the monolithic solution as a reference solution, but the idea was to interpret this as an input-output relation of these codes, where all nonlinearities are actually treated locally for each component. They don't spread, polluting the convergence of the entire system, the time discretization as well, and the conditioning of the algebraic system of equations also is not affected by the coupling of the model. So these particular three problems, for instance, the impact of nonlinearities, when we refer to this, imagine you have to solve a fluid structure interaction problem, but this converges in 3-5 iterations, and this is coupled to a very nonlinear ordinary differential equation model where your valves take longer to converge. So you are solving, in a monolithic approach, you are solving your entire system a lot of times, which are not needed, because what it is not converging is the valve dynamics, right? So regarding the time discretization, the same happens when you compare 1D and 3D. Maybe your 1D is an explicit solver, or maybe the stability condition of the 3D solver is, maybe no, it is independent of the 1D, so it is related to the characteristics of the three-dimensional model, and you don't want to attach the stability condition of one model to the other model because they are fully coupled, right? So we wanted to get rid of these kind of problems. Also, if you couple all these systems all together, you have to couple, for instance, for mass conservation, you have to couple all the nodes at these artificial boundaries with a single node from the one-dimensional model. This implies a very ill-conditioned system because you have a line in your matrix that couples one node with thousands of nodes, for instance, and this is also a problem at the algebraic level. So there are many issues that we wanted to get rid of, and the idea was very simple. So I will present this. We started discussing on this very simple one-dimensional heat transfer problem, where we wanted to, so the idea is very trivial, right? So, but it is very clever to go back to the trivial things and to explore these things more deeply. So the idea is that we want to partition this into two subdomains, where the transmission conditions, the coupling conditions, were the continuity of the main primal variable and the dual variable,
right? Here, the temperature, for instance, and the flux at point C, right? So, and we wanted to do this in a partitioned way. So we define a digital boundary for this left domain and a Neumann boundary for the right domain. This is one simple choice, but this is the choice that everybody takes when you talk about domain decomposition using Dirichlet to Neumann or Neumann to Dirichlet, and so on, this type of method. So you have this problem of coloring your domain. So where you define a Dirichlet boundary over the left, then you have to define a Neumann boundary over the right. And the idea was to try to generalize that. So in this case, for these choices, we define this operator. This is a flux operator, whereas by solving this problem with a Dirichlet boundary condition, you get the flux. So given a Dirichlet data, you get the flux. And on the other side, you have the dual operator, let's say, for the other domain, where by prescribing a Neumann boundary condition, you get the temperature at point C. So this is this kind, you have this kind of operator. And then you have two equations that are the transmission equations at point C that have to be verified to find the solution of the problem, right? So by solving this interface problem, I am actually solving the problem in a partitioned way. So in this case, this is a linear problem, but understanding the problem as this interface problem is a problem with two equations and two unknowns, where just because we wanted to, this is with a Dirichlet boundary for the left and with a Neumann boundary for the right. So the idea is to now to solve this interface problem solve this interface problem using any iterative method, right? You can use Gauss approach or Jacobi approach, and then you will iterate infinitely until you get the solution, or you can use a GMRS and you will get a solution in 2 iterations, right? So we are dealing with systems where these interface problems have a very limited number of unknowns because we are dealing with a one-dimensional quantities, real numbers, right, that must be equated at the interfaces between the 1D and the 3D or the 1D and the 0D. So the finite termination property of this GMRS or any other Krylov-based method is very, very interesting instead of a traditional Jacobi or Gauss-Seidel with relaxation approach, right? So the idea is that now we write the cardiovascular system as this interface problem, right, in terms of interface unknowns. So this input-output reasoning in terms of operators is the idea that we have for the black box paradigm. And in the case of the cardiovascular systems, is we are dealing with a nonlinear model, which is time-dependent. Well, we have to use a more sophisticated approach. In this case, we have been using Broyden approach with multi-time stepping strategy for dealing with the requirements of the different models. And in particular, if you understand now the model as coupling low pressure component, so this can be transported to the industry straightforwardly, right? Here we are talking about a living system, but this system of pipes is encountered everywhere in the industry. So we have here a low pressure component made of active components like the cardiac chambers and nonlinear components like the valves, cardiac valves. And there are in particular 3 interfaces that drain the blood from the upper body and from the lower body. The arterial system, which is a high pressure component, which has all the 3 interfaces with the low pressure component, and also may have other interfaces with any specific vessel component that I want to put inside the cardiovascular, inside the arterial system. So these interfaces connect with any 3-dimensional model, for instance. And a 3-dimensional model where all the interfaces of the 3-dimensional model are connected to the arterial system. So we needed this versatility to deal with many interfaces, to deal with, in the case of the fluid flow problem, pressure and flow rate quantities, which are the quantities I want to conserve, pressure resulting from the conservation of momentum, right? And flow rate from the conservation of mass. I will not go through the equations, of course, but this is for the low pressure component, how the equations look like. right? Cardiac chambers, cardiac valves, compartments where I have compliance, inertance, resistance, representing the different phenomena in these compartments. The high pressure model is governed by the one-dimensional equations of fluid flow in the formable vessels, which are also nonlinear because of the convective terms, are nonlinear because of the pressure area relation representing the behavior of the arterial wall, and also any specific vessel component where I have the Navier-Stokes equations in the formable domains as well. So here we can see that this is an Ale form of the Navier-Stokes equations. And the idea is to put this all together within the paradigm that we have assembled. So here we have this interface, the interface variables, which are pressure and flow rate at each one of all the interfaces which I want to connect, right? And this is basically the mapping, how these interfaces map into the corresponding components for the specific components, right? In the specific high pressure, low pressure, and specific vessel components. So in this case, we have to take some decision on what is going to be an input for each component, what is going to be an output. For instance, for the high pressure component, it was seen through many testing that pressure values, pressure boundary data was rendered the model better behaved numerically. For the low pressure, it was differently. We have better experience prescribing the flow rate at the inlets and pressure at the outlets. When I say inlet outlet, know that here there is no the concept of inlet outlet. Actually, in the venous side, yeah, inlet is where the blood is drained, and outlet is where the blood is ejected into the arterial system. But actually, in these kind of systems which are closed, there is not actually inlets and outlets, because the flow goes through the inlet and through any interface, forward and backward, depending upon the place where you cut your model. And for the specific vessel, which is Navier-Stokes problem, okay, the best strategy is to prescribe Neumann Neumann data, right? You don't have information about your velocity profiles. You have information about your flow rates or your pressures, which are assumed to be constant, to behave constant over the interfaces. So this is an homogeneous Neumann boundary data over each interfaces in these three-dimensional models. And as output, we have the dual variables, right? If we prescribe the pressure, then we get the output, as output, the flow rates. Where we prescribe the flow rate, we get the pressure, and so on. So this is what, with any system, when you prescribe one variable, you get as the dual, you get the other information as the result of your operator, right? So here, this input-output reasoning, here we are just coloring which was our choice. But again, this idea is choice-free. The same methods can be applied if I chosen, for instance, prescribing pressure instead of flow rate. So the method is not, the strategy is not constrained to the choice of the boundary data. Like in the one-dimensional case, I could have assembled the one-dimensional problem that I showed before with Neumann boundary data to both domains, subdomains, right? So here for the high pressure component, the pressure as input in these interfaces, and pressure as input also here, right? And as output, I get the flow rates. And I prescribe, note that I'm prescribing here the pressure over the high pressure component, and also the pressure over the three-dimensional model, right? Before following this strategy, what was found in the literature usually is, okay, prescribe pressure to the 3D domain, get the flow, prescribe the flow to the 1D domain, get the pressure, and so on. But this is very constraining when you have many interfaces, right? And when depending on the stiffness of the each component is that you will get a better condition model when you prescribe one or the other. But this is well known in the literature of domain decomposition. So the idea is to have now a set of nonlinear equations, which are these residual equations that can be written implicitly in this way in terms of input and output variables, or in an explicit manner. In a more general setting, they look like this. For instance, this approach also allows us to, for instance, to couple a 3D model, Navier-Stokes model, with a one-dimensional model by prescribing the continuity of the total pressure. For instance, suppose you want to continue to prescribe the continuity of the total pressure, then the total pressure has a static component, the dynamic component, and this is a nonlinear boundary condition. And you can do that by prescribing the Neumann, a traditional Neumann problem, to the Navier-Stokes problem. So you don't need to change your Navier-Stokes problem into a total pressure formulation for enforcing the continuity of the total pressure in the system, right? And this is something that may be wanted in this case, because where you have this wave propagation phenomena on the one-dimensional side, the total pressure continuity is a boundary condition that is also has also a strong significant meaning, right? So here I'm writing the equations openly, right? So these operators, all these operators are time dependent, right? Are nonlinear, all the three. Discretization is specific for each one of the models. So for instance, we use first order backward Euler in time for the low pressure component, with fixed point iterations for the valves, Crank-Nicholson second order approach in time for the one-dimensional model. In this case, we were using a least square finite element method over the characteristics. Currently, we're using finite volume, high order finite volume approach. This is with fixed point iterations for the nonlinearities, and a second order in time with an Ale formulation with some stabilization for the Navier-Stokes problem. But again, this is unrelated to the choices of the other components. So you can have different codes that talk to each other, that don't talk to each other. They just communicate with a master code that will send information, and this master code encodes this. For instance, this numerical approach here is a Broyden-like algorithm, particularly, where the residual is the assembly of the residuals of the different interface equations provided by the different components. And now we can start playing around with how we, for instance, assemble this Broyden tangent and drive the algorithm, right? So particularly, we perform Broyden iterations for what we call the outer iterations, which are how the system is strongly coupled, and the inner iterations, which are those performed by each component to evaluate the residual. Because we can evaluating this residual, you can use some iterative method until this residual is converged, or you can have some pseudo-linear evaluation, linearized evaluation of the residual, right? So here we have a global time stepping, which is a time step at which all the components communicate with the master to establish the coupling, to zero the residual equations, right? And the local time stepping, where each component runs until it reaches the time step where the communication must occur, right? So in this multi-time stepping approach, I will not go, of course, through this, but here I'm just drawing how these outer and inner iterations with the local time stepping, how this looks like. So this is where the different components run independently, right? And they communicate with the master, which sends boundary data and collects boundary data according to the choices that we have made, until the residuals are zeroed at each time step, and then goes next to the next time step for the next iterate, for the evolution in time, right? So this, we have made many testings. Here these results are just to show that even in a very simplistic setting of a 0D, the 0D component coupled with the one-dimensional component, so no three-dimensional model here, we can have gains, right? So this is the number of evaluations of the coupled system when we solve it monolithically for different time steps, global time steps. And this is the number of the evaluations that each component has for the different time steps when we consider different sub-time stepping, right? So this is the number of, so in this case, the most expensive model is the one-dimensional model, of course, and it took nearly 4,000 evaluations for this time step. This was for running per cardiac cycle, if I'm not wrong. But when we decouple, then we can reduce, was the best case, we could reduce the number of evaluations. In this case, particularly, we used a linearized evaluation of the residual for this one-dimensional model, but the total number of evaluations was reduced, considering a sub-time stepping for the low pressure component. So here we have a lot of evaluations for this very cheap model. But in this case, we are showing that even in the simplistic case of a 1D coupled to the 0D, we can accelerate, we can speed up the simulations, we have gains, and this speed up is magnified would be magnified if you had a three-dimensional model here in the monolithic solution, right? Because in the monolithic solution, you would have to solve the 3D model all the times until the entire system is converged. So in some cases where we increase the time step, the global time step where communication occurs, there is no convergence for the monolithic solution, but then we have convergence when we do this sub-time stepping, right? And in this case, there are, so of course, I'm not showing the results, so the result for the time step is a little further from the converged solution, right? But even you can increase the range of stability of the problem with respect to the time step choice. So these are some takeaway messages that I will not go through, but basically the sub-stepping allows to circumvent the issue of the nonlinearities, which remain local for each one of the different components, right? The number of total evaluations that I mentioned before in the case of one of the specific time step choices, right? And this was for a 1D, 0D simulation, which is supposedly fast. So you wouldn't have to have problems with this type of simulation. But again, when you put a three-dimensional model inside this 1D, 0D system, these speed ups, of course, would magnify. Here we are now introducing a three-dimensional model. So these three-dimensional simulations are of course, time-dependent and taking into account fluid structure interactions. So this over the left and over the right are the boundary data to this domain, and these are the boundary data over the other three interfaces where the 1D model connects to the zero-dimensional model. So we have 5 interfaces, 10 unknowns, and the multi-time stepping strategy. And here we are looking at the convergence history for 4 cardiac cycles here, for 4 cardiac cycles. So we can see that it is pretty insensitive in this case to the choice of the different time stepping strategies. Here are for different choices of the local time steps for the 0D and for the 1D component. Here are some numbers, but the idea is that the convergence history, the method is quite robust when we use these Broyden-based strategies. And the number of iterations, particularly in this case, was found to be smaller for this time step, right? But the total cost is, of course, smaller in the second case. So again, the number of iterations is sensitive to the local and global time step choice. Here we have a more complex situation with 5 three-dimensional models put at each one of the bifurcations in this model of the arm. So these are the main arteries in the arm. And we have 5 three-dimensional models with very different boundary data on all of them. So imagine if you would want to do that with a Dirichlet to Neumann approach, that could be an issue. Mostly in terms of the convergence of any relaxed Gauss-Seidel method. We have struggled with this type of problems a lot prior to these developments. So in this case, the time step is identical for all the components. Here are, for instance, the flow rate and the pressure for different components. Here you can see that the wave propagation in the system as you move far away from the proximal to the distal locations, and the history of convergence, insensitive, nearly insensitive to the flow regime, right? That's likely higher number of iterations here where the flow, the Reynolds number are higher, where the pressure increases, but nothing too impactful on the entire convergence history. This is another system where we have a single three-dimensional model with 7 coupling interfaces in a more detailed model of the arm. So in this case, yes, you cannot have any clue of how to set up boundary data for this type of model, because there is no way that you can measure pressure or flow rate in these smaller vessels. We are relying here on how the boundary data is set up at the distal locations and at the proximal locations of this arm model, where we prescribe a flow rate through the major vessel, and then we prescribe some resistance boundary data far away from the three-dimensional model. And what happens in the middle is taken into account by the physics of the one-dimensional model, right? So in this case, as you can see here, the pressure in green, the flow rate in red are very, very different, very, very similar. There is no direction predefined. So you have some collateral vessels here where the flow rate, you don't know a priori if it goes forward in the distal direction or backward. So blood can be returning here. You don't know that a priori. But again, the convergence, the strategy proved to be reliable in this problem. Again, we have a very, very reasonable number of iterations for the coupling of the entire system. Here we have 14 unknowns. So 14 unknowns in this nonlinear problem. Theoretically, if the problem was linear with GMRS, it would take 14 iterations to converge, right? This is nonlinear. This is time dependent, so the finite termination property is not, and it is subjected also to a lot of finite arithmetic issues. So the finite termination property is not verified, of course. Okay, these are just some snapshots of the three-dimensional flow, just to show a little bit the complexity of the problem we are addressing. And with this, we started addressing another improvement, which is extrapolation in time. So in the Broyden algorithm, we took the history of the solution from previous time steps and the history of the tangent from previous time steps. And then we come up with some extrapolation in time to improve the prediction of this tangent. And what we have seen, okay, this is standard, right? So we have seen that the combination of a third order extrapolation in time for in this case m was for the x and 0 was for the tangent, right? But we analyzed many combinations of these. So with this, it was like here. Okay, so with this extrapolation in time, we managed to reduce. This is also a very complex case where the flow rate is features the largest Reynolds numbers in the entire cardiovascular system. So this is a very challenging problem because also the boundary data differs a lot among the different boundaries. In this case, we are addressing this three-dimensional problem is also addressed in a distributed fashion. Right here, we have 15 coupling interfaces with 30 unknowns. Here we have all the major vessels in the aorta artery, and we tested different extrapolation strategies and see what happened with the iteration. So these are the boundary data, the resulting coupling data, right? So this is not actually boundary data. This is the result of the interactions between the 1D and the 3D. And this is the average number of iterations in one cardiac cycle. And you can see how you nearly cut in half the cost of the solution of this problem by exploiting this extrapolation in time. So this is how it looks like along the iterations. When you don't extrapolate here, this problem features some sensitivity to the regime of the flow, to the cardiac cycle. Right here are the two systoles and the diastoles. And here, when we extrapolate, then this sensitivity is reduced. Right? So there's some snapshots of the flow problem that we are solving there. So the takeaway message is that we can encapsulate into black box codes, or this black box idea in these computational hemodynamic simulations. Oh, sorry. So this is a very robust and flexible, because you are not tied to picking boundary data for any specific component. That will depend on the characteristics of the component. If it is better behaved with a specific boundary data or with a different boundary data. You may have coupling conditions which differ from the boundary data directly, right? Are not directly related to the boundary data that you can prescribe on your components, like in the case of the total pressure, and where you prescribe pressure for the three-dimensional problem, right? The Broyden approach was the one that proved. We tested different versions of Broyden, Newton, matrix-free Newton methods, GMRES, matrix-free methods, and the best we got was this Broyden algorithm. The multi-time stepping strategy is also naturally accounted for within the formulation. The temporal prediction improves the efficiency, and we have two levels of parallelism, where the component-wise parallelism, where you basically distribute your computing effort in different computers, this component to this computer, these other to the cluster, these other to the other computer, and then at the level of the component through traditional high distributed computing approach for solving, for instance, the three-dimensional model, right? And this allows us to run quite complex hemodynamic scenarios where you have different flow regimes in large vascular regions or multiple three-dimensional models, which is sometimes it's important because the three-dimensional model where you have some obstruction, for instance, or some anomaly, geometric anomaly in the model, that will affect the response of the cardiovascular system, and this will affect back the blood flow patterns, right? And this is in a let's say in a static situation regarding the boundary data over regarding the it's a boundary data. But imagine if I consider, for instance, control mechanisms acting over the systems. So if you introduce any change in either the 1D or the 3D, and this will trigger some control mechanisms, then you are accounting everything for within this coupled simulation. So these are this is the way that we strongly believe it is the most robust approach to computational hemodynamics. Surprisingly, it is not yet widely spread in the literature. So most people in the community still uses boundary data instead of putting the boundary data farther away from the model and getting less sensitive to the boundary data. So this type of approach, even if it is a state-of-the-art in coupling components, it is not widely used. People uses most rudimentary, let's say, numerical strategies to solve this boundary data problem. And the boundary data problem is the most sensitive issue in computational hemodynamics because of the large influence that they have on the predictions that you get from these models. So I would like also to finish the talk saying that Gustavo has been crucial in pushing these ideas. He has been very open and generous all the time, sharing these ideas and letting you working on these ideas that he dropped, and then the results are there. I think that Gustavo has been very pioneer in this field, has helped pushing forward this field, even if there is very strong people in the field working beforehand, but which didn't take this problem in the way Gustavo took it, and the simple. I would like to say that the way in which he put these ideas in such a simple way made me feel very, very stupid, because I mean you are talking about system of linear equations and GMRS and things like that, but you say, okay, there is no way this was not done in the literature before, but then you go and look for what had been done in the literature, and actually Gustavo had something there. So I would like to say that I am extremely happy of having shared this line of research with Gustavo. And there are codes at EPFL, at Politecnico de Milano, that are using these ideas that we developed here in Brazil, and then we transported. I worked with people there, and we transported there. So I think that the contribution is permeating much more groups than just ours. So I finish here, and happy birthday, Gustavo. Oh, okay. I have a couple of slides. So this has resurfaced today. I have forgotten about that. Not forgotten, but we this coupling has resurfaced from 1 year or 2 years ago, working with Rodrigo Paz from ANSYS and Hugo Luis Oliveira from Unicampi. And we are now working on coupling a 3D FSI cardiac valve with a closed loop model of the cardiovascular system to put cardiac valves into physiologically realistic scenarios, right? So this is all the comments that I made before, okay, in this case are taken to the extreme, right? Because the valves, the 3D fluid structure interaction for valves is a very complex nonlinear problem that requires very specific and robust solvers, like LS-DYNA, for instance. And we are working on coupling the LS-DYNA with a simple Python code, right? And where we understand here the cardiovascular system as a boundary condition provider. So this is how these things is such a state of the art that very powerful codes now are considering putting these ideas into their tooling box. So now, yes, thank you. This is how where the titles begin and then the film continues, right?
Thanks, Pablo. Any questions for Pablo?
Thank you very much, Pablo. Thank you for coming. Thank you for such a nice presentation. I wanted to say, I told you the first time, when I saw the Dirichlet to Neumann iterations that are done in domain decomposition, intuitively I call that Gauss-Seidel iterations. And that was intuition. And then in which formulation the Dirichlet to Neumann is a Gauss-Seidel presentation, and it was this formulation, and then we said, why solve by Gauss-Seidel? There are better ways. But I didn't know is that that thing of extrapolating, the extrapolation part I had never seen before, right?
Well, we work with Enzo on that.
Uh-huh.
Yeah, we presented in a conference where you are a co-author.
But I
And
I forgot that the
if I'm not wrong,
extrapolation
it's
part.
part of some of no, because we never published that simulation with the aorta. I just presented at the conference.
Because so the second matrix, you do not extrapolate. You leave it
Yeah,
like
we
that.
extrapolated, and we saw that the best result was without extrapolating.
No extrapolation.
Yeah, exactly.
But the initial solution, yes.
Yes, third order.
And it improves
Yeah,
significantly.
third order. With third order, we reduce from 5.2 iterations in average per cardiac cycle to 2.6.
But I think that my best contribution in this field was some time ago. You were here and you were doing the arterial part, the arterial network, and I told you, if you are going to do the arterial network, just do the best arterial network in the world, mais grande do mundo. And Pablo did that. So really, nowadays, if somebody wants to make a digital twin of a human cardiovascular system, it is his model that one should use, because he has this enormous digital twin of the body with the venous parts. How many arteries? 20,000 arteries.
No, 2,000, but each artery sometimes is split into vessels, and so
he has a function.
But 2,000 arteries that have a name. So we name 2,000 arteries.
Each one with they are in the circuit, right? That is amazing what you have done there, and to be able to create such a tool for the investigation of cardiovascular diseases, right?
Thank you.
Congratulations.
Any other question?
Forgive me if I make a very applied question. I noticed that your time step is very small. I mean, usually we take 100 time steps to do a cardiac cycle, and I noticed that yours is 0.002 or 0.001. So it's about 10 times smaller. You take 1,000 time steps to do one cardiac cycle. Why?
Well, our solvers are not yours. I mean, no, our solvers. No, the method is implicit. We are solving in a moving domain, and with the method that we implemented, we couldn't go over 400 time steps per cardiac cycle. So the 3D solver is not our the stronger part of our simulator. We have something that works pretty well, but it has some pitfalls in terms of time step choice. Of course, if we have had some better code, then you could go over the time step choice. So yeah, as a rule of thumb, we perform 500 time steps per cardiac cycle.
Okay, but my question is more, so it's not the 1D arterial system or the valves that are limiting the time step.
The time step, depending, because you can communicate the models at a larger time step, but internally you're running the 3D must be run at the time step such that it converges. So
it is the 3D that is limiting.
Yeah, of course, when you communicate the components at the larger time steps, then you will deviate a little bit from the true solution.
Yeah.
That's but if you are ready to pay for that, then you have to choose your local time stepping to go from one time to the next time, such that it is the best choice for your 3D code. And the choice for your 3D code is different from the choice to the 1D code. And this is limited by the constraints of each numerical method, but they are independent. So they are not if you ask me, what makes the system, the connected system, to diverge when we increase the time step at which the communication occurs? I would say maybe the zero-dimensional model with the valves, because when you go through opening and closing the valves, then you have some, exactly. So that's the most sensitive point. That's why you cannot communicate at two larger time steps. And also the extrapolation in time in this case does not solve the problem, because the problem is discontinuous. So, so it's a big issue, the valve problem, and how it affects the rest of the system. Such a small component pollutes the entire, all the numerical elegance of the rest of the system.
And if you're going to connect to LS Dyna, then your time step in this, at least in one of the systems, is going to be 10 to the minus 6.
Yeah,
because it's explicit.
Yeah, our Python code will be waiting for the,
okay,
for the LS Dyna to, But no one so far that I know has solved the 3D fluid structure problem on cardiac valves coupled to the rest of the system, putting the valve into some realistic environment, right? So because the valve definitely affects how pressure and flow rate waveforms will form upstream and downstream, and so when you change some of the components in this case, and you want to assess, for instance, a new valve design, that the idea came from a project where Gustavo and Hugo were interested in some designs of artificial valves, then you are not assessing your valve in the real state. You are assessing your valve in very artificial conditions.
Okay. Can I make a question?
Sure.
Roberto? Have you checked some of your results with a real person with echo Doppler studies?
Okay, that depends on, you cannot check all the results with the person because you have very partial information. I heard about the sensors, and you don't have such a detailed placement of sensors on the person. Most of them are non-invasive, so you have some ultrasound signals non-invasively acquired. Now, in heart failure patients, you are having this internal. This is there are some patterns where you have devices where you have catheters implanted with devices in your body, and this sends signals outside the body, and then you take decision upon these signals. So this is basically in line with what Professor Reinhardt said, these internally assessed digital systems. So basically, we have to rely on how we verify that the qualitatively and up to some point quantitatively the results of the model are, and you compare with the available literature, because the data, we don't have data. Here is a field where you don't have data, and the data, when you want to collect it, is very expensive and very risky to get the data. So we have to get with partial data in this case, and now we are working on calibrating models with but these are again heart failure patients where you have just point values of these signals, and these point values should be used, and we are using this for calibrating zero-dimensional models of the cardiovascular system, because you only have systolic pulmonary pressure, diastolic pulmonary pressure, cardiac output, which are just data points. They are not signals in time, and you have to take decisions with that. So we are now working on that, but the clinic requires, these tools are quite ahead of what can be used in the clinic, right? You try to understand some mechanisms and relate some, for instance, wall shear stresses correlate with this has been done, we had been done that. How shear stresses correlate with the development of plaques in the arteries, but this requires collecting data, which is very, very expensive to do. So, but we use some of the tools that I'm presenting here. And this machinery, in part, is being applied to actual problems in the clinic, not the entire machinery. So,
Okay, thank you again.
Just a small announcement. We have less than 2 hours to have lunch. There are some places nearby. But if you go and come back and then you wait there, it will be just